Hello, welcome everyone. Thank you for joining us at Edinburgh Instruments' first Spectroscopy in Action live webinar. My name is Paula, I'm the Marketing Account Lead at Edinburgh Instruments, and today I'll be joined by Angela, our Raman Product Manager, and Nikesh, one of our application scientists, and they will be telling you all about multimodal microscopy and 2D materials. Today, Angela is going to introduce and discuss multimodal microscopy and how it can enhance your research, and Nikesh will give a demonstration of multimodal microscopy on a 2D material sample using the RMS1000 Raman microscope and Raman software. At the end, we'll have a live Q&A session so you'll be able to ask any questions you might have. Hope you enjoy the webinar. I'll now pass over to Angela to get started.
Thanks for the introduction, Paula, and good morning or afternoon from wherever you're joining us from today. And as Paula briefly mentioned there, the webinar is going to be roughly split into two halves today. So the first half will be between myself and Nikesh, giving you a bit of the theoretical background as to why you would want to use these techniques on your samples. And then I'll be handing over to Nikesh, who's live in the lab, to show you how to actually set this up on the instrument. So please excuse any cheesy handovers between the two of us. We're just making sure this runs as smoothly as possible. And then the second half of the technique, we're going to deep dive into a sample of tungsten diselenide that we've analysed previously, which has a lot of interesting features for all three of these techniques. So quickly, I'll hand over to Nikesh, who will introduce the system and the first sample.
Hi there. So I'm in the lab with the RMS1000, the instrument that we're going to use for the multimodal analysis that Andrew's just mentioned. So one of the first things we're going to do is place our slide into the microscope. So here we have a slide of a molybdenum disulfide placed onto the glass slide. I'm going to now put this into the microscope stage itself, into the holder. Now I'm going to turn on the light source for the microscope. Currently, I'm set into bright field illumination, which we're going to use to help focus the sample. So now we're going to look around on the sample to find some flakes of the molybdenum disulfide. And here we've identified two very nice looking flakes of the molybdenum disulfide. The next thing I'm going to do is change it to the dark field illumination. And we're going to use this for the Raman imaging. So now we have our sample in focus and the microscope set to the correct conditions. We're able to run our instrument for the respective Raman, PL, and SHG measurements. Now back to Angela, who will explain the fundamentals of each of the techniques.
Thanks, Nikesh. So as it has been handed over, I'm going to quickly introduce you to Raman spectroscopy. So firstly, I'm going to tell you about the fundamentals of the technique and then what you'll actually learn about it when you use it. So in Raman, when we use a monochromatic laser source, it will interact with your 2D material, and most of this light is elastically scattered, which is called Rayleigh scattering, and that doesn't provide us any useful information. However, a small portion will undergo inelastic scattering, which we call Raman scatter. This arises from the interactions of photons with phonons, and during this interaction, the phonon energy changes, and this results in a frequency shift corresponding to your phonon energy. So Raman spectroscopy is directly measuring these frequency shifts of this, and it's in the scattered light. So this spectral analysis gives us a really detailed fingerprint analysis of your sample, of its material vibrational modes, revealing crucial information about how its phonon dispersion and fundamental lattice dynamics. So what does that actually mean for your 2D materials? So we can think of Raman as mapping your phonons. So what will it tell you? We can quite rapidly determine the number of layers present, and this is because the frequency of the Raman band, its intensity, and even the shape of the bands that we see are very dependent on the number of layers in your Van der Waals material. We can also identify defects. So again, structural imperfections will change the local vibrational environment, which in turn will change your Raman spectrum. So we can either see changes to your fundamental peaks, or we can even see the creation of brand new vibrational modes. And a prime example of this is in graphene, where your D band will only exist when there are defects present. So we can use Raman to map across your sample to see which areas are particularly high in these structural imperfections, such as vacancies, your edges, and your grain boundaries. We can also use it for strain analysis. So this will provide us information into the mechanical properties and eventually the device performance. We can look at doping and functionalization, which obviously both are critical to the end real world application of your 2D material. So we can check the homogeneity of that across a sample. And with that rapid fire description of what Raman can do for your samples, I'll hand back over to Nikesh, who will speak through us setting up a map of a 2D material.
Thanks, Angela. So here are the flakes that we identified during the microscope setup. So what we're going to do is we're going to establish a map area. So I've just drawn a line which creates this box, and then I'll define the number of spaces and the number of points of that map to define the map resolution. So what I'm going to do is I'm going to very quickly go through the measurement parameters, set up the map, and then I'll go through and explain each of the parts of the measurement parameters that we're using for this molybdenum disulfide Raman map. So one of the first things I'm going to mention is that for this material, I'm going to be using an exposure time that's less than 0.5 seconds. This allows me to use the fast map function. So this means that we can run a far quicker map than a standard map. So if I'd kept this in the standard mapping, this would have taken us 6 minutes for us to run. Now that I'm using fast mapping, we're actually getting this down to about 1.5 minutes. So for the measurement parameters, so for this material, we're using a 532 nanometer laser. Now, in general, for 2D materials and for molybdenum disulfide, 532 provides a good balance of a nice strong Raman signal as well as typically low fluorescence. So for 2D materials, it's quite important to use a high grating. Now, the highest grating that might be possible on a system. On the RMS1000 I'm currently using, I have an 1800 grating groove per millimeter grating present. So this means that I'm able to get the nice clear definition of the peaks and resolve them, which is important as we can see on the spectra, we have sort of the defined peaks for molybdenum disulfide. I've kept the other conditions that I'll mention. So I've kept the pinhole and the slit open to the maximum, and we can see that we're actually acquiring a really nice resolution of the flake itself. So when I did the measurement setup, you can see this yellow box that's active on the live acquisition of the maps. So I defined this and I placed this over one of the main peaks of the molybdenum disulfide. So this is a peak at around 385, and this is corresponding to the E2G band of the molybdenum disulfide, which represents the in-plane vibrations. The other main peak that I could have used to the right of it at about 405 was the A1G peak. Now, this is more for the outer plane vibrations of molybdenum disulfide, and that was another peak that I could have used. For this map, I've chosen to choose the E2G, so you can see that I've left that yellow box in the position where I would expect to see that peak. So we can see that we're coming to the end of the map. So now within the same software, I'm actually able to now process the acquired map. So we can see we've got some nice different spectra over the flake itself. And now I can begin to process the map itself. So I'll remove the pixelation. This makes it a little bit clearer for the image. And then I'm just going to change the actual maximum range. So then it's a bit more representative of the spectra that's there. So we can see very clearly that there are differences on this flake at different points of the flake. So it's important to use, we can use Raman, and in particular those two peaks that I mentioned, the E2G and the A1G. So we can determine the quality of the 2D material or molybdenum disulfide, as well as detecting any defects and strains. So now back to Angela, who's now going to explain the fundamentals of PL.
Perfect. So yes, on to spectral technique number 2, photoluminescence, or PL for short. So here we're now going to investigate how your 2D material will emit light after it's absorbed it. So the process begins with light absorption and excitation, where the photons with sufficient energy excite your electrons to a higher energy level, and these often form bound electron hole pairs. Subsequently, these excited carriers will now undergo relaxation. So they're going to rapidly lose energy through non-radiative process until they reach a lower energy state. The final step, which is our photoluminescence, is radiative recombination. So here the electrons in the holes recombine and they release some energy as photons. The energy that they release or emit is directly reflected to the energy's difference between the recombining states, which is then related to the material's electronic band gap. So by analysing the emitted light, PL spectroscopy provides crucial information about the electronic structure and optical properties of the 2D materials. So for Raman, we're probing your phonons and we're probing the vibrations. And in PL, we're now looking at your band gap. So what does this mean? So again, we can use PL to map the number of layers. So PL imaging will indirectly map layer number because the numbers of layers are will significantly affect the electronic band structure, which in turn alters the emitted light energy and its intensity. So this allows us to really easily visualize the thickness variation across a 2D film that you might have grown. Again, we can use PL to look at your defects and edge boundaries or edge effects. So defects and impurities will disrupt the electronic structure. And this often reduces the light that we're emitting, or it changes it. So we're either going to be looking at a reduction in intensity, or we're going to be looking at a slight shift in the peak itself. We can also use this for looking at strain. And so this is useful for mechanical strain because it will modify, again, the electronic band structure of your 2D sample. And this shifts the PL emission energy. So PL can be used to visualize these strain fields, and these can be induced by many things. So one is your samples will be really sensitive to the substrate that they've been grown on, or it can just be intrinsic material stress. And finally, again, similar to Raman, we can just check the uniformity and the environment that your sample is in, because your 2D material's light emission, again, will change depending on its surroundings. So this will include any nearby surfaces or what molecules you've actually attached on to your 2D material. So PL imaging tracks all of these changes across the material, revealing how its optical properties are affected by its local environment, which is obviously critical for then deciding, is this 2D material worthy of taking on to fabric to actually produce your device? Or is it actually not going to be giving the optical properties and electronic properties that you need it to function? So again, a quick whistle-stop tour of what PL can do for you. And now back to Nikesh to show how it can actually be analysed in the lab.
Thanks, Angela. So let's start with the PL mapping. So the first thing we should note is that the existing map area from the Raman map is retained within the software. So what we're going to do, we're going to lower the actual laser power that we're using because overall PL is a far more sensitive technique compared to Raman. So this allows us to use a lower laser power. So as I did before, I'm going to very quickly set up the map first of all, get that running, and then I'll break down each of the parameters that we're going to use during the setup. So yep, so just acquired a nice spectra here, and let's get this map started. So one of the first things that I should mention for PL, so what I've done is I've lowered the grating to the lowest that's available on the system. So for this instance, we're going to use on what this current RMS that I have is a 300 groove per millimeter. And this is just because PL, as I mentioned, is a far more sensitive technique, and we're only actually focusing on bands, whereas in Raman, we're actually looking at the particular peaks. So because I'm using a lower laser power because of the actual PL sensitivity, this means I can actually even use an even lower exposure time. So as I did with the Raman map, we're using fast mapping, and I'm actually using a far quicker exposure time than I was in the Raman map. So this is actually going to be even quicker than the Raman map that I previously ran. So for the PL measurements, I've stuck with the 532 nanometer laser that we'd used in the Raman measurements. Now, this is because visible lasers are generally a good laser for 2D material analysis, and it's in particular with PL as the energy matches well with the electronic transitions. So while this map is just finishing off, then we can begin to perform our post-processing. So yep, so we have acquired our nice map here. So if I begin to look at different regions of the flake that we identified, so I'm going to remove the pixelation like I did before, just to make it a little bit prettier. I'll actually change the color scheme here a little bit, and I'll make that just so something different so we can differentiate it between the actual Raman map. So we can see quite clearly that the PL map is matching very nicely with the white light image of the flake that we'd seen previously. So PL, as Angela's mentioned, reveals a lot of information. In particular, on this sample that we have here, we can see that where we have lower regions of PL, so these sort of darker purple regions, this is typically indicative of a greater layer number. The position of the peak itself can also indicate strain. So if we start to see a redshift in the peak, this could also show us potential of any strains that might be present on the flake. So now back to Angela, who will explain the fundamentals of the final technique that we're going to discuss today, which is SHG imaging.
Yeah, so we're now on to the third and final technique that I want to introduce to you, second harmonic generation imaging. So we're now moving on to a non-linear technique. So for SHG to work, we need to use a really strong laser. And certain materials will generate a small light out once they've been excited with this laser, which is double the frequency of the laser. So for example, if we're putting a 1064 laser onto the sample will give us 532 out. This frequency doubling effect is a direct result of how the material will interact with the light in this non-linear manner. And the very important row here, which is highly detailed on this slide, it will be highly detailed on my next slide, and Nikesh will go into a lot of detail about it, is that this material will only give an SHG response if it is non-central symmetric. So this means that our SHG is exceptionally sensitive to determine your material's symmetry. And this is, as will be explained a bit more detail by Nikesh, but it's really important for knowing how your layers are stacked. So this is, as I'm sure you all know, is important because depending on how your materials will stack will determine the actual final electronic properties of your material. So it's absolutely critical to know how your crystals are growing so that you can check that your synthesis is going as you expect, and that means you can finally functionalize and use these devices in a real world application. So, as I've said, and I will keep saying, crystal orientation, that's what we care about with SHG. So your intensity of your SHG peak and the polarization of it are highly sensitive to the orientation of your 2D material. In van der Waals heterostructures, like these 2D materials are, the different stacking relative to each other and the twist angle can all be determined by using your second harmonic generation. It's also sensitive to defects and edges, much like Raman and PL. So all three of those techniques will provide you with good information on any defects in your sample. A nice little illustration of some pancakes there has been included to try and further explain this idea of non-central symmetry. So what we can have in a monolayer is your monolayer will always be non-central symmetric. So what you can see here is we've essentially put a blueberry on one side of your pancake, and that is not balanced by the other side of the pancake. So this will always give an SHG response because it is not symmetrical. However, when we start to stack these layers, we can have many different options, obviously. So the first option we see here is where we have a blueberry on each side, and therefore we've created central symmetry. So this means that we will now diminish that SHG response to not exist at all. And then the other option of a two-layer system is that both the blueberries are on the same side. So you've essentially doubled the lack of symmetry. And that means we will double our SHG response. There are obviously other options as we start to get more and more layers, and we've got a really nice example of a tri-layer coming up when we look into our tungsten sample. But for now, I will show you the small changes that you need to make. Well, I'll hand over to Nikesh, who will show you the small changes that you need to make on your RMS1000 within the software to now take your second harmonic generation images.
Perfect. Thanks, Angela. So, as I said earlier, the same map area that we've looked at on this flake is retained within the software. The first thing I'm going to do is change the laser to our SHG laser. In this instance, we're using the 1064 nanometer laser, and I'm actually going to put the laser power back up to 100%. Overall, as Angela just mentioned, because SHG is a non-linear process, this is actually far weaker compared to, say, PL and Raman. So that's why we're using the highest laser power that we have present. So we can see that majority of the conditions that I'm going to actually use are pretty much the same as what we use in PL, but I'm just going to very quickly set this initial measurement off and get the map started. Okay, so the map started now. So as I mentioned, majority of the conditions that I use in PL are going to be the same conditions that I use for the SHG. However, so this is including the grating, the slit, and the pinhole. However, what I did change was the center wavelength that we're actually looking at. So because we're using a 1064 nanometer laser, I'm expecting to see a peak at around 532 nanometers. So you can see that I've put our yellow box for the active map in the top left. So I've put this over that main peak at 532. So as Angela's mentioned, SHG is such a useful technique when it comes to 2D material analysis. So it is a powerful tool, and especially when we have flakes such as molybdenum disulfide that has multiple layers, this allows us to understand the crystal symmetry that might be present on the flake. It allows us to determine the orientation of these crystals as well. And I'll further explain that in my later discussion. And then this also allows us to further identify any strains and defects. So this map should just be coming to an end in the next few seconds. Okay, perfect. So we've got the map finished. So just going to click on a few points here. And then as I did with the previous maps, I'm going to remove the pixelation. And I think I'm going to pick a rainbow color scheme for this one. Okay, so we can see quite clearly on this flake that we have differing signals of the SHG over the flake itself. So we can actually see quite clear domains, and we can actually see grain boundaries present on the flake itself, which aren't as apparent with Raman and PL, but we can see quite nicely there that we can identify different regions of SHG on this map. So I'm going to hand back to Angela, who's going to show us a high resolution version of the flakes that we actually have.
Great, so that concludes the live demo session of this webinar today. We will, however, go through another sample of tungsten in just a second. So as Nikesh highlighted, these are actually some much higher resolution versions of these 2D flakes that we quickly demoed there. And obviously we're just doing that in the interest of time, because I'm sure you all have better things to do than to just sit and watch a Raman, PL and SHG map acquired, even though in total these are still really fast maps, but even them taking 10 minutes, that would be quite a boring way to spend 10 minutes. So we will now go on to talk about a sample we have taken previously that has a lot of detail in it, and I'm going to hand back over to Nikesh. We're moving on to tungsten diselenide here. So we've changed both our transition metal and the chalcogen that's attached to it, and we will now look at this sample which has all three layers: monolayer, bilayer and trilayer. So yeah, Nikesh, do you want to talk us through this?
Yes, definitely. So yeah, this is a material, a 2D material of interest, as it allows, and it has unique properties in both electronic and sensing technologies. So what we're going to do is we're actually going to take a deep dive into this material, and we're going to use the multimodal spectroscopy techniques that we previously used for the molybdenum disulfide. And so yeah, so on screen now we can see a flake that we've picked, and we've got both the reflected and the dark field illuminations. So we can see there's some nice characteristics on this flake, but when we begin to actually run the techniques that I've mentioned, we can build a bigger picture. So we'll start with Raman imaging. So one of the things to note for tungsten diselenide in particular is that it has a degenerative phonon mode. So both the E12G and the A1G contribute to the main peak that is seen at 250 Raman shift. So generally, the rule of thumb is that for 2D materials is that when we see an increase in the Raman intensity, this is normally indicating that we see monolayer. So on this map in particular, we can see sort of the yellow, and sort of these yellow regions are most likely to come from a monolayer. When we have a decrease in the intensity, this is where we're most likely going to be seeing sort of your multi-layer. So in this sort of inner domain of that triangle there, we can see quite clearly that we've got sort of lower signal intensities. When we begin to look at the peak position, so this also tells a complementary story. So when we have a monolayer system, we see a standard peak. And then when we move to more multi-layer systems, we begin to see redshifting in those peaks. So we can see, similar to the peak intensity that we are seeing sort of in this inner domain, we are identifying that there is sort of redshifting occurring in that inner domain. So most likely in this inner domain, we're going to be seeing some sort of multi-layering happening. So one of the final things that we can do is Raman spectral matching. So now this is all match data, which is seen in Ramacore. Now this allows us to pick spectra on the map itself, and then it will then intuitively pick out all the spectra that match that exact spectra, and then we can begin to identify different areas on a map. So in this instance, we've identified three key areas. So in A, we can see that we have a spectra, and it's an expected spectra at 250. And as we've looked at the peak intensity and the band position, we can most likely say that A is probably contributed from a monolayer. The inner domain of that sort of darker purple region, so we've identified as B and C. So one important thing to notice is not only sort of the shifting in the peak position, but it's also this additional peak that we're actually seeing at 310. Now, we can see it highlighted on the Raman spectra in B and C. Now, it's very important to note that this peak will only appear on multi-layered systems and is symmetry forbidden within monolayered tungsten diselenide. So now we're going to move on to the PL imaging. So PL imaging actually tells a very similar story to that we see with the Raman imaging. So we can see that with intensity, that the higher intensity is normally indicative of a monolayer, and with a lower intensity is for multilayer. And as I mentioned, similar with the peak position, when we begin to see a redshift in the peak position for PL, this is also indicating that we are getting more to a multi-layered system. So we can also perform PL spectral matching like we did with the Raman. So with the PL spectral matching, we can actually begin to uncover a bit more of the story. So we'll start off with A, in region A in blue. So we can see in the bottom right, we have this nice PL spectra for tungsten diselenide. Now this shows us the expected peak that we'd want to see at about 780 nanometers. When we move to region B, so this red trace here, we can see that we actually have an overall decrease in the PL intensity, but we also have this appearance of an additional shoulder peak at around 870 nanometers. When we move to region C, so in green, we can again see that the PL is further decreased in signal intensity, but again, the overall peak position, or the overall peak, is shifted more towards the NIR region. Now we can use this information and we can, from literature, and we can then begin to assign the actual layer numbering to the crystal, and based on the spectra that is produced in the bottom right corner. So here we've now assigned that region A is of monolayer, B being bilayer, and C being trilayer. So the final imaging is that we're going to perform is the SHG imaging on the tungsten diselenide. So we're going to start off, and as Angela stressed, and I've also stressed in the previous parts of the talk, we're saying that SHG only occurs when there's no symmetry present. So monolayer will always be non-cytosymmetric. So they'll lack, as they lack an inversion center. So in region A, as we can see in the bottom right, we can see that we have an SHG signal. So then we can determine symmetry of multi-layered crystals based on the different stacking that can occur. So this can be either 3R or 2H. So when we start with the bilayer, this is being identified as 3R stacking. Now, this is where we have two layers that have the same orientation. Now, because we've increased the overall sample thickness, or the overall number of layers, this means that we're actually going to see an increase in the SHG signal. So we can see we've almost doubled that signal from A to B. Now, finally, when we look at the 2H stacking, which is present in the tri-layer system, this is where we have the presence of one of the layers being rotated 180 degrees with respect to the adjacent layers. Now, I've represented here one of the potential ways that this could be stacked for a tri-layer system. So in this instance, we can see that layer 3 is actually oriented 180 degrees with respect to the other two layers. Now, because of this rotation, we've now partially restored some of the centrosymmetry. And as Angela had mentioned, once we restore symmetry with the two pancakes, this is where we start to lose some of our SHG signal. So you can see that we've partially restored. So this is why we can see a diminished signal in C. So typically when we have 2H stacking, we either see no SHG or a really low to similar amount of SHG that you'd expect for a monolayered system. So overall, each of these spectroscopic techniques has provided us a wealth of information. We started with Raman, which provided us in identifying the monolayer and multilayer aspects of the flake. We then moved to PL, which again further was concordant in the Raman findings, but we were actually then able to identify and acknowledge the different layering present, so whether it was mono, bi, or tri. And then finally, with the SHG, we're able to get this crystal structure and understand the different stackings that are present on the flake itself. And all this information are complementary to each other and provide us with a wealth of knowledge for 2D materials such as tungsten diselenide.
Thanks, Nikesh. I have a quick conclusion here, but overall, Nikesh has given us a really detailed and thorough conclusion there. So, headlines: Raman spectroscopy excels at probing your lattice vibrations, aka your phonons. Photoluminescence is the primary tool for investigating the electronic band gap, and SHG comes in at the end to uniquely determine the symmetry within a non-centrosymmetric material. All of these provide information on defects and disorder. They can all help to identify any stress or strain. But by employing all of these, this ultimate triple threat of spectroscopy, you can gain a much more comprehensive understanding of the structural, electronic, and defect properties of your 2D materials. So this will be great for helping you determine if your synthesis has been successful or not, and how you might need to improve your synthesis. And it will help you give complete characterization of the material, and that will get us closer to the end goal applications of these materials. And with that, I'm going to conclude the sort of slides and demo that were given in this webinar, and I'll hand back over to Paula, who will ask us any questions that have come up whilst you've been watching.
Yes, thank you. So we actually have had some questions already, a few on software. So the first one is, you mentioned fast mapping. So is this unique to this instrument, the RMS1000?
So no, this is
no.
Until you
Sorry, Nikesh, I can take
Sorry.
this one.
Looking there.
Yeah, so we have, just really excited to answer any questions. We have two Raman microscopes actually. We've got an RM5 and an RMS1000. We've demoed you the RMS1000 today because it can do SHG. The RM5 can do just the Raman and PL, but it's still a great instrument if you don't have any interest in doing some second harmonic generation. Both of these instruments come as standard with fast mapping. So what we're doing with fast mapping is, instead of like stopping the stage at every movement, we're continuously moving the stage, and we're using our CCD camera way more efficiently to be able to do this a lot quicker. So it's something that is available on all of our Raman microscopes.
Excellent, that's great. And also, still on the software, what kind of software compatibilities exist for the export of data to allow users to use other data analysis software?
I'll take this one. So in terms of actually exporting data, so there's a magnitude of options that we can have. So we can do the standard CSV. So if you wanted to export this into Excel, we also offer so that it can be in an SBC file. So this then means it can go into third-party software such as like MATLAB or Python that people would typically use to further process their data.
Excellent, great, lots of options for people then. And also, what methods are used to calibrate the system, and how often is calibration recommended?
So within the software itself, so the recommended approach would be that we perform 2 calibrations a day. So initially upon startup of the actual instrument. So there's an internal calibration as well as the option to set up an external calibration as well. So the internal calibration allows us to run a silica standard. So this can be run with every internal laser that's available on the instrument, and that'll run against each of the gratings. So you can either pick and choose the individual lasers and gratings that you want to calibrate. I pretty much just set them all to be calibrated just because I change between lasers and gratings quite every so often. But yes, if possible, twice a day, I would say at least once a day would be advised.
Mm-hmm. Excellent, thank you. And now sort of moving to more technique-based questions. Which technique is most useful for determining layer number and why?
So for layer number, I would advise probably most likely to be SHG. So as we mentioned throughout the talk, and both me and Angela have said repetitively, like each technique is complementary where it kind of supports one another. You get slight subtle differences from each, but each kind of tell the same story. SHG in particular, as I showed in that last example, will show you the differences of the stacking, and then we can use that in concordancy with the PL, and we can then determine sort of layer number in that manner.
Excellent, thank you. And I think we'll just finish on one more question if there's no more that come in. What causes the redshift of the main Raman peaks as the layer number increases?
It's a very good question. My understanding of it is that it's to do with the electronic bands themselves, because we're increasing the thickness or the actual number of layers. This then causes that shift, and when we once we actually perform the process that Angela had shown for PL, this means that there's more sort of expansion of the electron holes, and then therefore more of a response, and we see that slight shift to sort of the redshift.
Yeah. Thank you, Nikesh. So if there are hold on, there's just one more question. Oh wait, just one more question just came in there. So Robert had said on the screen you could see a polarizer and analyzer installed. What level of polarization control does the system have?
Great. So on the system we've just demoed, we do just have a 1/2 and 1/4 wave plate in both the laser path and the scatter path. However, we do have the option of 360 polarization, which we've not shown in this webinar. We will be doing a sort of separate series on that, because obviously explaining polar plots is an additional complexity for explaining how this works. However, yeah, completely agree that 360 polarization is going to be extremely helpful for your Raman data and also for that SHG data, because by doing the 360 polarization, we can now actually determine, earlier on when Nikesh said it could be 3R 2H stacked, or it could be 2H 3R stacked. By controlling your polarization, you can actually determine the correct way that these are stacked, rather than just looking at the peak by itself, which isn't just sensitive enough just by looking at that peak.
Thanks. And actually, there's just one more came in just as you were speaking there. So the stress straining mapping is the intrinsic stress straining mapping, or does the instrument have capabilities of external stress?
So what we can do is you can actually you can add on essentially more analysis tools onto the instrument. So you can add an additional stage which just slots into our mapping stage, where you can apply different forces and stresses onto your sample. And so we work with Lincoln on these sorts of stages. So they do have a stress and strain inducing stage that we can use. We've had that in the lab before. They also make temperature stages. So you might want to cool your sample down, actually, especially in 2D materials, because when we cool our 2D materials down, we're going to get a much nicer PL response. And another thing we can actually do on the RMS1000 that we didn't show today is measure your photoluminescence lifetimes as well. But these are going to be longer when we're using lower temperatures. So that is definitely another great tool for looking at 2D materials on either of our systems, is being able to decrease the temperature and yet also apply stress and strain to your sample, so it's not just inherently to how it's been grown. Again, so you can determine how your device is going to perform.
Excellent. Thank you. Okay, so I think that concludes our webinar for today. Thank you, Angela and Nikesh, for presenting and telling us all about 2D materials and multimodal microscopy. So this webinar will be published on YouTube for you to watch and share with any colleagues who you think might find it useful. And we'll also be continuing our Spectroscopy in Action series throughout the year, so make sure you're subscribed to our YouTube channel or signed up to our mailing list to get all the information first. And so thank you to everyone for joining us. We hope you enjoyed the session and found it useful, and we will see you next time.